Hello everyone. Today we will be talking about convergence of series. We have already seen some preliminary tricks by which we can check for convergence. For example, a telescoping series. Okay. So today we will be seeing three formal tests by which one can check whether a given series is convergent or not. Okay. So let me start with the first test known as comparison test. We will first state the criterion, then we will show how it works, that is we will prove validity of the criterion, and then perhaps we'll see an example. Okay, so let me state, let summation an and summation bn be series of non-negative reals okay, so both these are non-negative series. Assume that an is less than or equal to bn for every n. Okay, then if we have this relationship that an is less than or equal to bn for every n, then we have three different scenarios. If summation bn is convergent, then summation an is also convergent. That is, if the bigger series converges, then the smaller series also converges. Second criterion says, if summation an is divergent, then summation bn is also divergent. That is, if the smaller series diverges, then the bigger series will also diverge. So we have these two criterion, that is, if the bigger series converges, then the smaller series converges, and if the smaller series diverges, then the larger series also diverges. So we will first prove these two results, and then we will see one or two examples. Okay, of course we will again use the definition of convergence of series via convergence of partial sums. Okay, so let Sn and Tn be the sequences of partial sums corresponding to series an and bn respectively. So an is less than or equal to bn for every n would imply Sn is less than or equal to Tn for every n. Okay. Now we further know that summation. So if I want to prove part 1 first, then in part 1 it is given to us that bn is convergent, summation bn is convergent. Okay, so summation bn is convergent implies Tn is a convergent sequence. we have already proved in sequences that every convergent sequence is bounded. Okay, therefore Tn is a bounded sequence. Tn is a bounded sequence implies there exists an upper bound. In fact, we are assuming that an and bn are non-negative. As a result, summation an and summation bn are increasing. So Sn and Tn are monotone increasing sequences, and we have proved that a monotone increasing sequence converges to its least upper bound. So T belonging to R is an upper bound for Tn, and if it is least upper bound, then Tn converges to the same T. So T is an upper bound for Tn means Tn is less than or equal to T for every n, and we already know Sn is less than or equal to Tn. So this implies Sn is less than or equal to T for every n, and Sn is also a sequence of non-negative numbers. Therefore Sn is, and not just non-negative, because ans are non-negative, Sn is also a monotone increasing sequence. So Sn is a monotone increasing and bounded sequence, and we have proved that if a monotone sequence is bounded, then it is convergent. Okay, so therefore Sn is convergent. Sn is convergent would imply summation an is convergent. Thus we have proved that if summation bn is convergent, then that implies summation an is convergent. Okay, let me prove the second part of the comparison test. In the second part, we say that if the smaller series diverges, then the bigger series also diverges. Okay, so what is given to us is summation an is divergent. So if we continue with the same notation, then that would mean that Sn is an unbounded sequence. Okay, the corresponding sequence of partial sums is unbounded. This implies given any real number m in R, we can always find at least one Sn larger than that m. Okay, given any m belonging to R, there exists n naught in n such that Sn naught is greater than or equal to m. Okay, not just that, because ans are positive, Sn is a monotone increasing sequence. So Sn naught is larger than m would actually mean Sn is larger than or equal to m for every n greater than or equal to n naught. And we know Tn is larger than or equal to Sn. We have used it in the earlier proof also. So Tn will be larger than or equal to Sn will be larger than or equal to m for every n greater than or equal to n naught. Okay, and this is, we are saying it for every m this happens, means given any m we will always find infinitely many points beyond that m. Okay, thus Tn is a divergent sequence. Okay, therefore Tn is a divergent sequence, because we know that if a sequence converges, then all but finitely many points are inside the neighborhood, and here we are saying that all but finitely many points are above a certain point. Okay, thus we have proved comparison test. So one simple example for comparison test, we have proved that the harmonic series diverges. Okay, 1 upon n, summation 1 upon n diverges, that we have proved. What we know is that 1 by root n is always going to be larger than or equal to 1 by n. Okay, therefore by comparison test, summation 1 by root n must diverge. Okay, part 2 of the comparison test. In fact, not just that, summation 1 by n raised to p, for any p less than 1, same result will hold. Okay, so this will diverge by comparison test. Okay, so far. So this is an application of part 2 of the comparison test. Let us check for part 1. So suppose I have summation 1 by n square. Now from 1 by n, I cannot say anything about 1 by n square because 1 by n square is smaller. If a bigger series diverges, that doesn't say anything about the smaller series. However, for 1 by n square, what we can do? We can write 1 by n square is smaller than or equal to 1 by n into n minus 1 for every n greater than or equal to 2. Can you see this? Because 1 upon 2 is less than or equal to 1 upon 2 when 1 upon 2 square. So 1 upon 4 is less than or equal to half. Then 1 upon 3 square is less than or equal to 1 upon 3 into 2. 1 upon 4 square is less than or equal to 1 upon 4 into 3, and so on. Okay. And we have proved that this type of series converges. Actually, we have proved 1 upon n into n plus 1. But basically, these are the same series. Okay, just the notation is different. We have two consecutive terms in the denominator. Okay, so we know that summation 1 upon n into n minus 1 converges. Hence, by part 1 of the comparison test, we conclude that summation 1 by n square also converges. Okay, and if 1 by n square converges, then I can again use comparison test to conclude that 1 by n raised to p for every p greater than or equal to 2 converges. Okay, because it will always be smaller, and hence by comparison test it will converge. Okay, so this is the statement, proof, and an application of comparison test. Okay, let me now go for next test, which is known as ratio test. It is also known as D'Alembert's ratio test. Okay, so D'Alembert's ratio test. So we will follow the same style. Let me write the statement, then we will prove it, and then we will see one or two examples. Okay, so let summation Cn be a series of positive reals. Let summation Cn be a series of positive reals. Since the name is ratio test, we have to deal with ratios. So assume that limit over n Cn plus 1 upon Cn is equal to r. Okay, limit over n Cn plus 1 upon Cn is equal to r. Then the series summation Cn is convergent if r is between 0 and 1, 0 is less than or equal to r is strictly less than 1, divergent if r is greater than 1, divergent if r is greater than 1, and the test is inconclusive if r is equal to 1. The test is inconclusive if r is equal to 1. Okay, let us try to prove this first. So we have to prove that if the ratio converges to r, then and if r is less than 1, then the series is convergent. Okay, so let us try to prove this part first. So what I know is limit n going to infinity Cn plus 1 upon Cn equal to r, and 0 is less than or equal to r is less than 1. Okay, now I have 0 here, 1 here, r is somewhere here. So I can always find some s which is between r and 1. Okay, for example, I could take r plus 1 by 2. So choose s belonging to r such that r is less than s is strictly less than 1. Okay, now what do I know? Why do I take this s? What we know is Cn plus 1 upon Cn, limit is r. So Cn plus 1 by Cn belongs to r minus epsilon to r plus epsilon. Okay, so if I choose this s in such a way that it is beyond r plus epsilon, means basically see this works for every epsilon. So I choose epsilon which is say half of this distance between rs, then Cn plus 1 is by Cn is always less than or equal to s. That is Cn plus 1 is always less than or equal to Cn into s. Okay, so we are going to use this result. So choose s in r such that r is less than s is less than 1. Now given epsilon equal to mod s minus r by 2, so we are making sure that r plus epsilon is smaller than s. Given epsilon equal to mod s minus r by 2, r plus epsilon will be strictly smaller than s. Okay, therefore there exists a knot in n such that Cn plus 1 by Cn belongs to r minus epsilon to r plus epsilon, because it's a convergence sequence, for every n greater than or equal to n naught. For this choice of epsilon, I find a knot such that Cn plus 1 by Cn belongs to r minus epsilon to r plus epsilon. So which means Cn plus 1 by Cn is less than or equal to r plus epsilon for every n greater than or equal to n naught. And we have chosen epsilon in such a way that r plus epsilon is less than s. Therefore, Cn plus 1 is less than or equal to Cns for every n greater than or equal to n naught. Okay. So in particular, Cn naught plus 1 will be less than or equal to Cn naught into s. Okay. Then Cn naught plus 2, I can say, is less than or equal to Cn naught times s square. Okay, we will resubstitute. So in general, Cn naught plus k will be less than or equal to Cn naught into s raised to k. This is true for every k greater than or equal to 1. Okay. What does it mean? This means that summation Cn naught plus k going from 1 to infinity is less than or equal to Cn times summation sk, and s is less than 1, so this is a geometric series, so this is a convergent series, and hence by comparison test this also converges. Okay, I know what we have to talk about is summation Cn n going from 1 to infinity. Right now we are talking about summation Cn n going from n naught plus 1 to infinity, but if that n naught plus 1 to infinity part converges, then the remaining C1, C2 up to Cn naught are finitely many terms, so their addition is anyway finite, hence the total series converges. Okay, thus we have proved part 1, that is if r is less than 1 then the series converges. Now what happens if r is greater than 1? If r is greater than 1, then r is somewhere here, 1 is somewhere here, so again I can find some r minus epsilon to r plus epsilon such that r minus epsilon is to the right of 1. Okay, we can always choose epsilon in that way. Then all but finitely many terms of the sequence will be here, that is they will be greater than 1, so we will use that. Okay, so choose epsilon greater than 0 such that r minus epsilon is greater than 1. Okay, that is epsilon should be greater than r minus 1. So given this epsilon greater than 0, there exists n naught in n such that Cn plus 1 by Cn belongs to r minus epsilon to r plus epsilon for every n greater than or equal to n naught. Therefore, Cn plus 1 by Cn is larger than or equal to r minus epsilon for every n greater than or equal to n naught, and is r minus epsilon is greater than 1 for every n greater than or equal to n naught. Therefore, Cn plus 1 is greater than or equal to Cn for every n greater than or equal to n naught. Okay, in particular, because so Cn becomes an increasing sequence after n naught, so this implies Cn plus 1 is greater than or equal to Cn naught for every n greater than or equal to n naught. Therefore, summation Cn is greater than or equal to summation Cn naught, but this is a constant series and hence it is divergent series. Therefore, by the earlier comparison test, summation Cn also diverges. So if r is greater than 1, then the series diverges. Now for I equal to 1. For I equal to 1, why does the test fail? So test fails or test is inconclusive means we have both the possibilities. So consider Cn equal to 1 by n. Then limit of Cn plus 1 by Cn is 1, and we already know that summation 1 by n diverges. On the other hand, if I consider Cn equal to 1 by n square, then limit of Cn plus 1 by Cn is again 1, but summation 1 by n square converges. Hence, when the ratio is 1, the test cannot conclude anything. Okay. Let us take one small example. For example, consider a series 7 raised to n plus 1 divided by 9 raised to n. Okay. So my an is 7 raised to n plus 1 upon 9 raised to n. So an plus 1 upon an would mean an plus 1 will be 7 raised to n plus 2 divided by 9 raised to n plus 1 into 9 raised to n divided by 7 raised to n plus 1. So this gave me n plus 2, n plus 1. So 7 remains and then upon 9. Okay, 7 by 9. This is less than 1. And hence by ratio test this series converges. Okay. By ratio test, D'Alembert's ratio test, the series converges. Now the last test that we will study is Cauchy's root test. Okay, so we have studied comparison test, we have studied ratio test, and now we will study Cauchy's root test. So again, let me write the statement, then we will prove the result, and then we will apply it to one or two examples. So let summation an be a series of positive reals assume that limit an raised to 1 by n is equal to a. So assume that this sequence converges, n raised to 1 by n, it converges to a. Then, so this is nth root, hence the name root test. Then the series summation an is convergent if that limiting value a is between 0 and 1. It is divergent if a is greater than 1, and the test is inconclusive. The test is inconclusive if a equal to 1. Okay, so the root test also fails if the root turns out to be, limit of the root turns out to be equal to 1. Let us first prove this criterion. So suppose we have limit an raised to 1 by n equal to a with a less than 1. Then we have to prove that it converges. Okay. We will again use slightly similar trick. So what I know is a is less than 1. So I can always have another real number alpha between a and 1. Okay, it could be a plus 1 by 2. So choose alpha such that a is less than alpha. Therefore a raised to n is less than alpha raised to n. Okay, and what is a raised to n? A raised to n is actually a n because it is nth root, I mean in the limit. Okay, So we can say that in the limit means again there exists a knot in n such that a n is less than alpha raised to n for every n greater than or equal to n naught. Okay, a n is less than alpha raised to n for every n greater than or equal to n naught. And now alpha raised to n is again a geometric series with alpha less than 5. So geometric series converges, therefore by comparison test summation a n converges. Okay, now we have to show for a greater than 1 it diverges. We will again use a similar proof. So when a is larger than 1, so now I have a greater than 1. This case a greater than 1 means limit is greater than 1. So again after a certain point everything will be in a minus epsilon to a plus epsilon, that is everything will be to the right. Okay, therefore there exists a knot in n such that a n is larger than or equal to a minus epsilon for every n greater than or equal to n naught. Okay, a n is larger than or equal to a minus epsilon for every n greater than or equal to n naught, and a minus epsilon is already greater than 1. Therefore a n is larger than or equal to 1 for every n greater than or equal to n naught. Okay, therefore summation a n greater than or equal to n naught is larger than or equal to summation 1, which is a constant series. So this diverges implies this diverges. So this is still a, so this becomes a divergent series. And now for the third case, why does the test fail or stay inconclusive at r equal to 1? So again we can use those same example, 1 by n, 1 by n square. Both these will give you value of ratio to be 1. However, one of them converges and the other one diverges. Hence the test fails at 1. So what is the use of root test? So again there are many places where convergence of a series can be easily checked via root test. One common example is what is known as power series. So if I have something of the form summation a n r raised to n, okay, so this is known as power series. You have seen power series perhaps in PGF. So summation a n r raised to n. So by geometric, so here we can apply root test. Okay, so if I apply root test, what do I get? So nth root of this entire term, so if I call this entire thing as Cn, nth root of this will be nth root of mod an into r. So nth root of mod an raised to r. Okay, so this would look like nth root of mod an into r raised to n, which is nothing but nth root of mod an into r. So we know this will converge if limit of this is less than 1. Okay, so this converges if limit over n going to infinity nth root of mod a n this converges if this into r is less than 1, that is r is less than 1 upon nth root of mod a n. Okay, so this r is also known as radius of convergence for the power series. Of course, this is in the limit. Okay, thus the the root test gives us a nice tool to examine convergence of any series of this type, summation a n into r raised to n. Okay, so let me stop here. Thank you.